Good day again. Evan Snyman from Local, making the difference. Again, we're going to look today at some more examples from Euclidean geometry. These are all examples from past exam papers, and I won't lie to you, some of them are going to get quite difficult towards the end. So I hope you follow with me. Cool. So again, let's read through the text. O is the center of the circle PRST. Again, let's mark it for the moment. We do have a diameter in play here. We don't have any lines going to any chords, and we do seem to have an angle coming off that diameter. Okay. TR produced intersects SV in V. Yes, I can see that. And ST bisects PTR. The meaning of that word bisecting there is that therefore these two angles are equal to one another. So we know that T1 equals T2 because they tell us that ST bisects that angle. We are told that TS is equal to SV. And again, realizing that if I have an isosceles triangle, there's an implication to that. And that is that, oh, that's really cool. It means that V is also equal to T1 and T2. So we have a really cool little extra fact coming out from just reading the text, that those three angles are all equal to one another. TOP, OS, and SR are joined. Those aren't too fussed. So now we need to go and answer the questions. And 10.1, again, I know that I've copied this over without giving the mark allocation. The mark allocation of only 1 or 2 marks will tell you that 10.1 really is straightforward. How big is PST? Well, PST is this angle over here. Again, I like this 3-letter system because it tells you it comes off the chord PT. If I go look at the chord PT, I realize that the chord PT is a diameter. So if I have a diameter and an angle coming off it, it should follow that PST equals 90 degrees angle from a diameter. 10.2, determine the size of S4. Well, again, let's have a think about it. Okay, S4 is this angle over here, and I don't seem to have a lot of information about it, so I need to probably do some thinking about it to get there. Okay, it looks as though it is probably in the vicinity of 90, but looks can be deceiving. So, and we know that there's a caveat, a warning on the front cover of the exam paper always, that the diagrams are not necessarily drawn to scale. So that's probably not a great idea to say it's 90. I'll be very happy if it ends up being 90, but as I said, it's probably not a great idea just to state that it is 90 without doing any work. Okay, what I do know is that I have one, again, they told me that there was a circle PSRT, and that should have said some warning signs going off. If I have 4 points on circumference, that means I've got a cyclic quad. And so if PSRT is a cyclic quad, it should follow that this angle here is the external angle to that cyclic quad. It is outside the brief of the circle, and TV is a straight line, unlike S, the angle S4, which does not involve a straight line radiating out of the circle. So what I now have is R2 is the same size as P, external angle of a cyclic quad. I have that V is the same size as T1. So if I was to say, let's have a look here, and let's see if we get this done a little bit more easily. If I was to say, let T1 equal X, we'd get that T2 equaled X, and we'd get that V equaled X. We would then get that this red dotted angle is 90 minus X by 3 angles of a triangle. But we know that this red dotted angle is the same size as R2, so that is 90 minus X. And it does give us then that S4 does equal 90. Our initial reaction, our initial gut feeling was actually held out to be correct. So, as we've done before, we wrote it down on the diagram once for ourselves. we now need to track it through and write it down for the examiner. So let's go for it. We said, let T1 equal x, therefore T2 equals x, because it was given to us that ST bisected ST bisects PTR. We then had, therefore, V equaled x because of the isosceles triangle with TS equaling SV. It followed that, therefore, P equaled 90 minus x by 3 angles of the triangle with the right angle in it from earlier, so of triangle PST. And it then followed that R2 equaled 90 minus x, exterior angle of cyclic quad. And the cyclic quad here was PSRT. And as a result, S4 equaled 90 degrees. 3 angles of triangle RSV. Again, the mark allocation of probably about 5 marks would give indication that this is probably around about the right length of proof. And so that should make us feel a little bit good about what we've done here. Okay, I want to see some quickly. No, it's not. Cool. We now want to prove that these two triangles are similar, and we are now slowly but surely getting better at this because we have got some experience in what we are doing. So one thing we've been saying is mark it in. So if we are talking about these two triangles, we are talking about TSO, which is this one here, quite central, and we're talking about triangle TVS, this entire one over here, partly inside, partly outside the circle. And again, we should be able to see that we have got this one quite quickly because we've got angles that are equal. We've got that in TSV, we've got 2 angles equal to x. And in OST, or TSO, we have 1 angle equal to x at the moment, but we know that angle that point O is the circle center. So going through this one quite quickly, 10.3 in triangle TSO and TVS, 1 T1 equals T2 equaled x given, 2 V equals x equals S2. And the reason why S2 equals x is because we have an isosceles triangle based on the radii coming out from the circle center O. So again, let's put it in here. We have that equal to x because of isosceles triangle, radii OS equals OT. So we know, actually, let's go grab the green pen quickly, and we know that therefore that is equal to x because of the radii marked over here. So therefore these two triangles are in fact similar by 3 angles. Again, depending on your province, check if you need to put in the third angle. Therefore triangle TSO is similar to triangle TVS angle, angle, angle. Okay, what comes from this now is quite an interesting question. 2vs squared. Now we've seen a lot with vs squared, with ab squared and things like that, but to have one with a 2vs squared is slightly unusual, and probably the reason why I picked this question. So let's have a look here. 9.4. 2vs squared, so it's this one here, vs squared, that one marked twice. pt, which is this bottom one, this entire diameter over here, and tv being this entire piece over here. Okay, how are we going to get there? Well, we've got that these two triangles are similar. So let's have a look here. They're talking here about, so let's go from these triangles being similar and write down the proportion statement. So TS over, so the first two over the first two. So TS over TV equals the outer two TO, it's TS again, equals the last two SO over VS. Okay, I'm going to go over to the question and help the question guide me. They are talking here about TV. TV is this one here. So I want to use the left-hand one. And they talk to me about VS, which is over here, which is this one here. So I'm going to choose to use, I'm going to choose to use this one here. So I'm going to choose to ignore, I've got this one correct. I hope I do. Okay. I'm going to choose to use that one there. Okay. So I hope I'm doing it correct. TS, well, we know that TS is the same length as SV. So we've got SV over SV times, well, actually we've got TS squared. Okay, so actually let's go quickly, where's my eraser? Up here quickly. Okay, cool. So let's quickly go and have a look here. I'm saying to you that therefore we know that TS squared equals TO times TV. But the good news is we know that TS is the same length as SV, which allows us to make the conversion to SV or VS as we have it over there. But we also hopefully should recognize that the question is talking about PT, whereas we've got TO. So the question here talking about PT over here, whereas we are talking about TO over here, we should hopefully get that PT is twice the length of TO. In other words, TO is half the length of PT. And when we do that, we get our answer out coming quite quickly. So we get SV squared equals a half PT times TV. And if we just take that half across, we get the 2 SV as required. We get our final answer of, therefore, 2 VS squared equals PT times TV. And so that question, as I said, had something interesting in it, in that there was that coefficient of the 2, which was slightly unusual. We are now going to move on to my third example. Again, slightly unusual in that this one has what is called 2 internally tangential circles. There's 2 circles that are touching each other at a common tangential point, that being this point over here somewhere at M. Okay, so these 2 things have a common tangent. Okay, I'm again going to choose to mark that tangent because it is important. Okay, so if they touch internally, we have got that NK is the common tangent to this diagram. A, E, and C are points on the larger circle, which means immediately I've got 4 points on the larger circle. B and D are points on the smaller circle, but that means I've only got 3 points on the smaller circle, not 4. Which is a bit of a, well, makes it slightly easier because it'll be a little more difficult if I had 4 points on the smaller circle as well. We've got chord CA produced outside the circle to point K, which is on the tangent. We've got triangles drawn, and we are told that let NKB equal X. And so again, I'm going to quickly find KMB. So this entire piece here, not just the one piece, but that entire piece there has been labeled X. Can we find 4 other angles each equal to X? Well, I think the color coding here makes it quite easy, because if KM is marked as a tangent, then X is an angle between a tangent and a chord. If I look at the big triangle, at the big circle, then the chord would be EB. If I was to look at the smaller circle, then the chord would be MB. And so I can use those two to at least get 2 of the 4 quite quickly. So 9.1, using chord EB, is that ECM equals X, tan chord, the chord here being EM, and the theorem. And if I was to look at the smaller triangle, I would have tan chord that D1 equaled X, tan chord, and the chord here is BM. Okay, so again, advice, mark things in on the diagram. So that's an X, and that is an X. Okay, cool. Again, I'm having a moment just to scan around the picture. Okay, we have that those are equal. It does then follow that certain things are, that those two lines are parallel, but that's probably going to come out later. Okay, I see there's 9.2.1. Okay, and right now I'm kind of trying to role model to you what to do if you can't get full marks. And so at the moment, I'm only seeing 2 of the 4 angles that I need to prove are equal to X, not all 4. So what I'm trying to do is I'm trying to scan through the diagram and have a look. Okay, so, might come back to it in a moment's two's time, and that's probably a good exam technique to do, is to, when in doubt, move on and not waste too much time on things that you can't do. Tan chord. Okay, so what I'm going to do quickly is I'm going to quickly fill in 9.2.1. As I said, we've already been able to spot quite quickly that 9.2.1. Therefore, ECM equals D1 equals X. Therefore, BD is parallel to EC, corresponding angles equal. What we may need to do is look at why A2 equals B2. Okay, I can see why A2 equals B2, so again I'm going to proceed and hope that the rest of the question reveals itself to me, because as I said, at the moment I'm being quite honest, I'm trying to role model what to do if you can't do something in an exam. Well, if you've got B2, we know that B2 is going to equal angle E. So if you look at 9.2.2, B2 equals E, corresponding angles on parallel lines. We've got that that E equals A2. Okay, these are angles from the same chord CM. And therefore we've got that B2 equals A2 as required. Okay, so we now have that those are all equal to one another. Okay, I'm still not seeing quite why we've got this situation. Okay, but I do want to move on to 9.2.3 and have a look at what happens in 9.2.3 when we look at this proportion. And they're talking here again, we've seen me using a similar technique before. Okay, they're talking here about, I want to quickly erase these other lines here so we can see what I'm about to indicate more clearly on the diagram. So I'm just going to take those out of the picture. They're talking here about the highlighter, sorry about that. Cool. ME, the entire length, times MD, with MC, the entire length, with MB. So what I'm looking for now are 2 triangles that involve 2 of these lines each. And I think it's not too difficult to realize that the top triangle here involves MB and MD, whereas the entire triangle, MEC, involves the other 2. And so what we have is we have 9.2.3 coming out quite quickly. That 9.2.3 in triangle MEC and triangle MBD. 1 ECM equals D1. Sorry about that last one. Proven above. We have 2 that E equaled B2. Proven earlier, proven above. And therefore we have that the triangles are similar. Sorry about the handwriting. Angle, angle, angle. And from that, it follows that therefore ME over MB equals MC over MD. And as a result, ME times MD equals MC times MB as required. Okay, I'm going to have a moment to think about this and I'll get back to you in all of a few seconds' time. Please bear with me.